Hi guys, and welcome to this quick description for units 34 and 35. This is just before the midterm, so you guys need to know that the units that we covered up to this point, which are up to unit 35, will be part of midterm 1. We will have a live meeting. I will send the invitations. Hopefully you guys will attend to go through the midterm and all of the topics that are covered in the first exam. Let me share with you the screen so that we can see what we're covering in units 34 and 35. So basically, the units deal with the entire solar system as an entity and its structure, and also its origins. Okay, so the solar system is made up, of course, of 8 planets and the sun. By far, the sun is the main component of the solar system. If you compare, if the solar system was, for example, a vehicle, then the entire sun is the vehicle, with the exception probably of a wheel or something, and that is all of the other planets. So of course we have the sun, and then the planets. There are 2 types of planets: inner planets, and that includes Mercury, Venus, Earth, and Mars. And you also have outer planets, and the outer planets include Jupiter, Saturn, Uranus, and Neptune. In addition to that, you have the dwarf planets, and the dwarf planets are a lot. Some of them are actually inside the orbits of the planets, like Ceres, which is between Mars and Jupiter, and you have other planets, other dwarf planets, mainly in the past Neptune, called in the zone called a TNO, trans-Neptunian orbits. So TNO stands for trans-Neptunian orbits. Planets, basically, as the region of the solar system that is past Neptune. And that includes Pluto and Eris, Makemake, Haumea, and other dwarf planets. So that's part of the composition of the solar system. With the exception of the Earth and the inner planets, all the outer planets and also the dwarf planets have moons, okay? Earth has a moon also. Mars has 2 tiny captured asteroids, if you want to consider them as moons. In addition to that, you have part of the solar system. You have the zone between Mars and Jupiter. There is a region there that has asteroids called the asteroid belt. And that is what actually Ceres is located, okay? The dwarf planet Ceres. Okay. Then past Neptune, in that region, there is a Kuiper belt. That is also a main composition of the solar system. And then at some 50 AUs, 50 astronomical units and beyond, you have the Oort cloud. The Oort cloud is sometimes the source of some of these comets that visit the sun from time to time, but most of the times they're coming from the Kuiper belt. Anyway, these are some of the compositions in terms of the solar system. All of these objects, they orbit the sun in more or less the same orbit. So you have the sun in the center, and you have the planets and the dwarf planets. And they have also the asteroids that are both in the between Mars and Jupiter, and also in the Kuiper belt, and also in the Oort cloud. The difference between the Kuiper belt and the Oort cloud is the Kuiper belt has actually part of the flattened structure that seems to orbit the sun. Now the Oort cloud is distributed in and out of that plane, okay? Because it's far away from the sun, for the gravity of the sun to influence it that much, and that's why the distribution is more of a spherical shape than that of the Kuiper belt, which is situated somewhere in here, okay? Now, because of this structure, that suggested that there is some mechanism that led to them, and that mechanism is the conservation of angular momentum. When an object is in motion, it has momentum. When an object is rotating, it has angular momentum because it's going in a circle or circular path, more or less. So according to Kepler's laws, these are not actually, for the most part, they're not actually circular, but they're actually elliptical with their eccentricities defined from the previous units. Anyway, so this is one aspect of this motion. The second aspect of this motion, how these objects rotate or go around their axis. For the most part, all of these planets spin in the same direction as they are going around the sun, with a major exception of two of them. They all have tilt, though, more or less exaggerated, with the exception of two. One of them is Venus. Venus seems to be spinning in the opposite direction, whereas it's moving in the same direction as everybody else, it's spinning in the opposite direction. So it's revolving around the sun counterclockwise, like everybody else, but spinning clockwise, meaning the sun on Venus rises in the west and sets in the east. So the sun rises in the west and sets in the east, as opposed to everybody else. That is one exception. The other exception also is Uranus. Uranus seems to be spinning at 90-degree angle with respect, so this is its axis of motion, then this is its revolution around the sun. So again, there is an exception in here. It's not exactly 90, but roughly almost 90. And the same thing, this is not exactly 180, but very close from it. So it seems like early on, when the solar system has formed, everybody was spinning and revolving in the same direction, with the exception of something that might cause this two planets to spin in other directions, and that is the early bombardments and the early collisions all of these planets were engaged to, including the Earth, by the way, which is tilted at 23.5 degrees from the axis. In other words, the Earth also is going around the sun like this, but it's not spinning exactly in the same direction. It's spinning actually at this angle around this axis, which makes a 23 degrees, 23.4 degrees with respect to the plane with which it's revolving. So this is something that needs to be explained. And for the most part, all of this motion can be explained with the conservation of angular momentum, except in the event that some early events cause these planets to change their rotation. Okay. So this is another point of this unit that you guys need to be aware of. Finally, there seems to be also another correlation in here between the structure of these planets and also how far they are from the sun. As I was saying, the inner planets are inside. So here is the sun again. So there is a region in here where all the inner planets are, and that includes Earth. So the inner planets are Mercury, Venus, Earth, and Mars. After that comes, of course, Jupiter, the outer planets. Then you have Neptune, Uranus, and Pluto, and Uranus, and then Neptune. Okay, so those are the outer planets, and then, of course, all the objects similar to them. In terms of density, the objects in here, so these are the outer. These are denser than these objects. These are less dense. What I mean by density is the ratio of how much mass, can you put inside a given volume. Because of the fact that you have more materials for the same unit of volume, this for the same unit of volume will weigh heavier, I should say. And this is because of their structure. They're mainly made out of iron and heavy metals, basically nickel, and also silicate. Silicate are components that involve basically what is rock, basically. So rock and silicate are the composition of this. This, on the other hand, are either gas or icy planets, I'm sorry, icy objects in general, because we're not just dealing with planets, because also we have other objects in here. I'm sorry, I just should have mentioned in here when we were talking about the motion, of course, I forgot to mention the fact that the moons revolve around the planets, okay? And they also, for the most part, are moving in the same plane. except there are some exceptions for the faraway moons, which can be interpreted as captured objects, okay? So during the early interaction of the solar system, some of these objects, they get moved around back and forth, and when they are captured wherever they are captured. But the early structures, they are in the same planes. As a matter of fact, for example, when you look at the Earth's moon, although we'll talk about its origins. So here is how the Earth spins around its axis. The moon, for the most part, is within 5 degrees up and down with respect to this plane where the Earth is basically going. So it's also in the same plane. So all of the objects seem to be in the same plane, and this is due to this big factor that I was talking about. So in terms of density, this is basically in terms of density of the planets. It really tells me about the structure of this object more than anything else. Iron and nickel and metals in general, they have high densities, and that's why you have this object are denser than the others. By far, the densest objects in the solar system, they start from highest to lowest. The Earth is the densest object in the solar system in terms of the planets, followed by Mercury, and then in the bottom, you're going to find Saturn. As a matter of fact, the density of Saturn is less than 1, which means that it's 1 gram per cubic centimeter, which means that Saturn would float in water because the density of water is 1 gram per cubic centimeter, if there is an ocean big enough that you can contain it in it. The density is usually measured in kilogram per cubic meter, or also kilogram per liter, or also grams per cubic centimeter. They're all equivalent. There is a conversion factor between each and every one of them. Okay, they are not the same quantity though. For the case of the Earth, for example, it's around 5.5 grams per cubic centimeter, or 5 tons per cubic meter. So this is in terms of structure, in terms of density, in terms of properties. How do we know the age of the solar system? Well, we use a method using radioactivity. Materials on their own, for the most part, with the exception of a few of them, they are radioactive. If you take a kilogram, for example, of a substance called the parent, after a certain amount of time, that kilogram of substance will be shrink by half to 500 grams of one substance. So I took 1 kilogram, and another 500 grams of another substance. So basically, this is the remnants of the parent. So this is called the parent. So this is the parent still, 500 left from it. And then you have something called the daughter. And I'll explain it with an example in here. So the time it takes to go through this process, if I take 1 kilogram, is a half-life. So for the case, for example, of potassium, the symbol of which in chemistry is K, it can break into either calcium or argon. It's not only one path for the radioactivity, it could have more than one. For the case of potassium, it has 2 possibilities, but the vast majority is this one, and only 11% is this one. So the point being in here is, if I can measure how much the ratio of this parent is left versus how much the daughter is left, I can tell how long this material has existed before it went through this process, because this process is not terminated in here. Again, this parent is going to, after another half-life, is going to be only 250 grams left from it. And now 3/4 of a kilogram, or 750, is going to be the daughter. And again, if I wait another half-life, so this is after another half-life. Half-life in radioactivity is using the Greek letter tau. So this is the Greek letter tau. Okay, so after another tau, 250 is left grams. After another tau of that, only 125 grams, and so on and so forth. Okay, so if I can determine the ratio, so now from this one, I will have 875. from the daughter. If I can determine how much of this ratio of these two, I can tell how many taus have lapsed. And that's exactly the process that we use for dating in geology, using radioactive dating, or actually using it also for carbon, for example, for living organisms, because carbon-14 and carbon-12 also have a similar cycle where we can basically determine that ratio, those ratios, and once we find them, we will know how old the object is. With the exception of carbon, is of the order of thousands of years, whereas this one for potassium of the orders of millions of years. So this is what was used to determine the age of the solar system. How did the solar system came to be? Is basically using the nebula theory. So sometime around 4.5 billion years ago, the gas that spread about 3 light years, which is a huge distance, started to coalesce due to force of gravity. And as objects can get closer, as this object was in here, and now gets closer to the center, it loses potential energy in favor of kinetic energy. In other words, it's going to move faster. And as it moves faster, as it gets closer because of the force of gravity, it's going to move faster and faster. And as it moves faster and faster, its temperature increases further and further. So this is where the sun formed in the solar system. And this is also where the planets started to form and other objects started to form in what is known as planetesimals. Those are the early nucleations, if you wish, of the planet. And then after that starts to gather more and more material. Until at some point, the temperature in the core of the sun became so high that nuclear fusion started in it, and in which case it's going to expel a lot of these materials basically and starve everything, all of the other planets from further growth. So this is basically how the solar system formed. And again, as the material started to come closer and closer together, it's moving faster and faster, moving in the same direction. And hence, that is what I was talking about in terms of conservation of angular momentum, that everything was moving in the same direction. And everything was revolving in the same direction, spinning in the same direction, until those collisions basically started to move things, started to change that rotation a little. That's what we saw in the case, or that's what we see in the case of the solar system. Again, planets, when they form, they're a mixture of different materials. And because of the heat that is generated in them, the heavier materials, which is mainly iron, is going to move to the core. And the lighter material, in the case of the Earth, is going to be more stay in the top. And that is why you see the silicates and rocks basically in the upper mantle and the surface of the Earth. Whereas inside is the iron and nickel, basically the heavier elements. So this is what happened on the Earth. This is what we believe also happened in all of the other planets. So the process is called differentiation, where basically the heavier elements settle in the bottom and the lighter elements settle in the top due to the heat and the different motions that are involved, the convection, especially due to the heat. Okay, so what the convection is the process of motion of fluids or gases in general due to the difference in temperature. The core is hot, the surface is cold, here is denser, here is lighter because of the heat, and so the material that is dense starts to fall in, the material that is hot starts to move up. And this is exactly the bubble that forms during the if you are heating a liquid in your home, for example, on the stove. After you reach a certain point in here, the bubble starts to form and starts to go around. And this is basically the process is called, through which this is going around is actually called the, I lost the word in here for a second, okay. The word has to do with the transfer of heat. As I was saying, there are several mechanisms of transferring heat. One of them is radiation, and that is not the case. The other one is conduction, and that's not necessarily, this is not the case. Also, this is a process that happens also on Earth and the planets. The word is actually convection, okay? So that is when the fluid starts to move up and down, in this case, due to the difference in temperature, and that is because of the density changes. Okay, so Let me get back into the screen. So again, this is basically how the planets form. How the gases form actually is through, how the atmosphere form is through processes that involves volcanism or impacts. When the Earth formed, when the planets formed, they were subject to a heavy bombardment early on in the solar system because of the debris that is left from the formation of the planets, and the interaction of these different planets with this debris was sending the materials back and forth, and for a period of time, the planets were under heavy bombardment during that time. That causes two things. First of all, the materials evaporate, and that's part of the atmosphere that basically breaks it down into its components and evaporate. And that's how basically carbon dioxide, water also was brought in, and also oxygen was formed later on by the biological activity that starts to form on the planets, like the Earth, the case of the Earth. But that's how basically CH4, also methane, and all of the other elements also came in. Now, the other process is also volcanism. When volcanoes erupt, also they release a lot of these gases that are trapped in the rocks. So this is in a nutshell the two units. If you guys have any questions, please let me know.